Hi, in this video, I'm going to guide you step by step on how to use the I4I Local Metal Loss Screening Tool for API 579 Part 5. The link to the tool is in the video description, and this video is meant to be used together with the tool. API 579. Part 5 exists because not all thinning is general metal loss. In refineries, we often see localized thinning that is concentrated in one area, like a thin patch near a nozzle, thinning under a pipe support, erosion at an elbow, or a groove cut by high-velocity flow. Local metal loss can control failure even when the surrounding thickness looks healthy. Part 5 gives you a structured way to screen whether your case can be handled using Part 5 methods or whether you have triggers that require a higher rigor fitness for service path. Before we start, I want to explain two key Part 5 terms in a simple way. An LTA means a local thin area. That is a patch where the length and width are the same general order of magnitude. A groove-like flaw is long compared to its width, like an erosion groove downstream of a control valve. This shape matters because Part 5 treats these differently. Also remember that Part 5 is not just compare minimum thickness to T-min. Part 5 requires you to define the footprint, understand proximity to discontinuities and welds, and in many cases perform supplemental inspection to ensure you are not missing crack-like damage that changes the failure mode. Now here is how to use the I4I screening tool. You will answer every question from 1 through 32 by selecting yes, no, or NA. Use NA only when the question truly does not apply. Do not use NA because you are unsure. If you are unsure, that's a sign you need to gather more information before you can confidently screen the equipment. After you answer all questions, click the button that says check if FFS is needed. The tool will give you a result. When it indicates FFS is needed, it does not mean you failed. It means the screening found credible conditions where you need a defendable engineering basis rather than guessing. Now let's go question by question with refinery scenarios so the logic becomes clear, but I'll keep it moving so this stays practical and not overly long. Question 1 asks if the damage is best characterized as local metal loss, not general thinning. A realistic refinery scenario is a crude overhead line where most readings are healthy, but a small region near a dead leg or drain shows a much lower thickness than surrounding metal. That is local metal loss. Another scenario is erosion at the outer radius of an FCC slurry elbow, where upstream and downstream pipe is much thicker. If your thinning is clearly localized, select yes. The question 2 asks if you can classify it as either an LTA or a groove-like flaw. A realistic refinery scenario for a groove is a long, narrow thinning downstream of an orifice plate or control valve. A realistic refinery scenario for an LTA is a corrosion patch under insulation on a short section of pipe. If you can classify the shape, select yes. Question 3 asks if the damage is actually a gouge from mechanical damage. Have you redirected to the correct procedure instead of Part 5? A realistic refinery scenario is a drop tool or forklift damage leaving a long scrape that includes cold work. That should not be treated as normal corrosion thinning. If it is a gouge and you will handle it correctly, select yes. If you are trying to treat a gouge as local metal loss, select no. The question 4 asks if pitting is the dominant mechanism. A realistic refinery scenario is sour water service, where deep scattered pits control the minimum thickness. If pits are driving the minimum, that points you toward a pitting-focused evaluation rather than treating it as one smooth LTA. If pitting is dominant, select yes. If your thin area is smooth and patch-like or groove-like, select no. Question 5 is an important early screen. It asks if the metal loss is still within the specified corrosion or erosion allowance, and you still have enough thickness for future corrosion allowance to the next inspection. A realistic refinery scenario is a monitored piping circuit where the minimum thickness is still above the allowance limit and trending says it will remain acceptable until the next inspection. In that case, you record the data and keep monitoring, and no Part 5 assessment is needed right now. If you are within allowance and future allowance is covered, select yes. If not, select no. The question 6 asks if the component was designed to a recognized code or standard. A realistic refinery scenario is B31.3 piping or an ASME Section 8 vessel with drawings and design conditions available. That gives you a defendable basis for minimum thickness. If the design basis is unknown, your screening becomes weak. If you have a recognized design basis, select yes. Question 7 asks if the equipment is not operating in the creep range. A realistic refinery scenario is extremely high temperature service like heater outlet piping where creep can control. If creep is credible, Part 5, Level 1, and Level 2 are not the right tools. If creep is not a concern for your case, select yes. The question 8 asks if brittle fracture susceptibility has been addressed when relevant. A realistic refinery scenario is local thinning on a low temperature system where toughness is uncertain and cold startup is credible. If brittle fracture could be a concern, you should address that before relying on metal loss conclusions alone. If toughness concerns are addressed or not applicable, select yes. If not, select no. Question 9 asks if the local metal loss exceeds or is predicted to exceed allowance before the next scheduled inspection. A realistic refinery scenario is an erosion-prone elbow where the minimum thickness is close to the limit today, and trending shows it will drop below the limit before the next inspection. That is when you do the assessment now. If it will exceed allowance before the next inspection or already does, select yes. The question 10 asks if you have a thickness profile, meaning a UT grid, scan, or mapping sufficient to define the footprint and thickness variation. This is a critical Part 5 concept. A few spot readings are not enough for local metal loss because you can miss the true minimum and you cannot define the footprint. If you have mapping that defines the boundaries and the pattern, select yes. If you only have a few points, select no. Question 11 asks if you have the key thickness inputs: nominal thickness, allowance, future allowance, and your minimum measured thickness. A realistic refinery scenario is you have the drawing thickness, your corrosion program basis, corrosion rate trending, and a defensible minimum thickness from the scan. If those inputs are known, select yes. The question 12 asks for an LTA. Have you defined the footprint dimensions and projected growth to the future inspection date? A realistic refinery scenario is a thin patch that is a certain size today, but you evaluate it at a larger size in the future because corrosion can expand the footprint. If you can define the footprint today and at the future date, select yes. The question 13 asks for a groove-like flaw. Have you measured groove geometry and orientation, including if it is angled? A realistic refinery scenario is a helical erosion groove that wraps around the pipe as it runs downstream. If you ignore orientation, you can underrepresent the effective dimensions. If you have measured groove geometry and orientation properly, select yes. The question 14 asks if you have a method to establish groove base radius rather than guessing. A realistic refinery scenario is a groove that looks smooth but has a sharper root than expected. Root radius matters because sharp grooves behave like stress razors. If you measured it rather than guessing, select yes. Question 15 asks if you determined distance from the flaw to the nearest major structural discontinuity, such as a nozzle, support, attachment, or transition. A realistic refinery scenario is thinning close to a nozzle reinforcement pad weld or thinning at a pipe support where local stresses are different. If you accounted for proximity to discontinuities, select yes. Now we reach a group of questions that are really about one big idea: Local metal loss near welds can hide crack-like damage, so the screening makes sure you did the right supplemental inspection. Question 16 asks if weld seams inside the recommended box around the LTA and the flaw surface were examined using appropriate surface and crack detection methods. A realistic refinery scenario is local thinning near a longitudinal seam weld. If thinning is close to welds, you should not assume there are no cracks without checking. If you did the needed examinations, select yes. Question 17 asks if any weld seam segment inside that box is also thin. Have you done the appropriate volumetric examination as recommended? A realistic refinery scenario is the seam weld in the thin region is also below required thickness, so you add UT or RT to check for embedded defects. If you did the needed volumetric checks when applicable, select yes. The question 18 asks if crack-like flaws or unacceptable porosity are found, did you repair or redirect to a crack-like flaw assessment instead of continuing as metal loss only? A realistic refinery scenario is surface examination finds a linear indication near the thin region. That is no longer just thinning. If you handled that correctly, select yes. Now we shift to deciding what assessment level your case really needs. Question 19 asks if the component is a Type A component under internal pressure only, which supports Level 1 intent. A realistic refinery scenario is a straight run of pipe or a straight shell region with no significant bending loads controlling. If your case is internal pressure only, select yes. If the local stress state is dominated by weight, supports, nozzle loads, or external pressure, select no. The question 20 asks if the local metal loss can be represented for Level 1 by a single representative thickness and simple footprint dimensions without large variations or many thin islands. A realistic refinery scenario is one single patch with consistent thickness across the footprint. If that describes your case, select yes. If the profile is irregular and varies strongly, select no. Question 21 asks if the region shows significant variation or multiple closely spaced thin areas. Are you prepared to do Level 2 using thickness profiles? A realistic refinery scenario is a long, thin region with thickness changing significantly along its footprint. Level 2 helps avoid misleading simplifications. If you are prepared to do Level 2 when needed, select yes. The question 22 asks if external pressure or supplemental loads are significant enough that you should not rely on Level 1 internal pressure only assumptions. A realistic refinery scenario is local thinning near a saddle on a horizontal drum where weight bending is important, or thinning near a nozzle with large piping moments. If those loads are significant, select yes. Question 23 asks if geometry or complexity suggests Level 3, meaning complex shapes, complex loads, or failure of Level 1 and Level 2, where numerical stress analysis is expected. A realistic refinery scenario is a thin region at a complex transition with reinforcements and nozzle loads. If complexity points to Level 3, select yes. The question 24 asks if for Level 1 you have the required inputs ready, meaning the footprint dimensions, minimum thickness, and the distances needed for spacing and discontinuity checks. A realistic refinery scenario is you can clearly state the footprint size at the future date, the minimum thickness, and how close it is to the nearest discontinuity, all based on measured data. If you have those inputs, select yes. The question 25 asks if it is a groove. Do you have groove base radius data needed for groove screening? A realistic refinery scenario is a sharp root groove downstream of a restriction. If you have the base radius data, select yes. Now we cover a special but common refinery case, blend grinding. The question 26 asks if the local metal loss is the result of blend grinding used to remove a crack-like flaw. A realistic refinery scenario is grinding out a surface crack at a weld toe and leaving a blended depression. If that is your case, select yes. The question 27 asks if blend grinding was used. Did you recheck with surface NDE to confirm no crack-like indications remain before treating it as metal loss only? A realistic refinery scenario is performing PT or MT after grinding and confirming the crack is gone, then using thickness mapping to evaluate remaining wall. If you rechecked properly, select yes. Now we close with decision intent and follow through. The question 28 asks if your intent is to determine acceptability or re-rating. A realistic refinery scenario is operations needs to run to the next turnaround, so you may accept as is, temporarily re-rate, or define an operating limit based on assessment outcome. If you are making that accept or re-rate decision, select yes. The question 29 asks if you have corrosion or erosion rate estimates and footprint growth rates to support remaining life estimation. A realistic refinery scenario is you trend corrosion rate and you also notice the thin patch footprint expands over time, not just deepens. If you have enough data to project remaining life rather than guess, select yes. Question 30 asks if level 2 indicates not acceptable as is, have you considered the available paths? Reduce pressure or loads, repair or replace, improve weld efficiency with additional examination, or proceed to level 3. A realistic refinery scenario is a thin patch fails at current pressure, so you consider a temporary reduced pressure limit, a local repair, spool replacement, or level 3 analysis if needed. If you have considered these next step paths, select yes. The question 31 asks if you defined an in-service monitoring plan matched to remaining life and uncertainty. A realistic refinery scenario is shortening the next inspection interval and requiring repeat mapping on the same grid, so trending is defensible. If you have a monitoring plan matched to the risk and uncertainty, select yes. The question 32 asks if documentation will capture everything needed. Flaw identification, inspection profiles, NDE results, assessment levels selection, conclusions, and any operating limits or re-rates. A realistic refinery scenario is saving scanned files, grid layouts, photos, MT or PT reports, and the final integrity decision in the permanent equipment record. If documentation is complete, select yes. Now let's talk about what the final result means. If the tool indicates that an API 579 Part 5 fitness for service evaluation is likely needed, that means your answers show credible local metal loss that exceeds allowance or missing inputs or inspection gaps or applicability limitations. That is where you gather the right data, define the footprint at the future date, confirm weld and crack-like flaw examinations where needed, and proceed with the correct Level 1, Level 2, or Level 3 path. If the tool indicates that a formal Part 5 evaluation may not be required, it means the condition is within allowance and future allowance thickness is adequate, or you did not trigger screening concerns based on your current answers. But it does not mean the equipment is safe forever. If corrosion rates change, the footprint grows, conditions change, or you plan re-rating or extended run length, you should rerun the screening. Let me close with the most important takeaway. This tool helps you avoid the dangerous habit of guessing when you see a local thin patch or erosion groove. It forces you to confirm the damage type, confirm whether assessment is needed based on allowance and projected future loss, confirm you have real thickness profiling and flaw sizing, confirm you are not missing crack-like damage near welds, and confirm you are choosing the correct assessment level. Used correctly, it becomes a practical, repeatable gate that tells you when it is time to do the deeper engineering work before you continue operating, re-rate, or defer repair decisions.